Hey guys, welcome to the next section. It's all about continuous. But it's not quite all about continuous. And the reason for this is, let's suppose we just want to measure how much people weigh. Well, there's only a finite number of people in the world. But the fact of the matter is, there's some people that weigh very little, say a baby born as little as 1 pound. And some people can weigh up to 500 pounds. But in between here, we seem to get tons of examples of people all over the place. Now, we could easily gather, let's say, 20,000 pieces of data, and we still could make a bar chart. But in reality, it's not really discrete. You can throw a dart at any number and you can find somebody that is extremely close to that weight. So we're really not talking about a discrete set of values, but we can't know all of them. It's like knowing every digit of the square root of 2. Probably impossible. So let's think of the following simple example. You've got a dartboard. You throw a dart at it. And we only count the ones that hit. And so we have a center point, and we hit there. We have a distance, d, away from the center. Now, if we're throwing it randomly, just lobbing something at it in some way that we don't say there's really any bias or anything like that, it would seem that this distribution somehow starts at 0 and goes all the way up to r. And does it look like this? What is its shape of a bazillion dots? It becomes a continuous function, and every value is allowed. And it seems that the ring of one distance has more dots on it than a ring at a smaller distance. So it seems like maybe it should be going straight uphill. How can we describe this? And here's the other strange thing. Since there's like a bazillion dots here, what's the probability? Let's say x equals 1/2. Seems like it's got to be 0 because it's 1 over like everything. So it doesn't make sense to think of these things in a discrete fashion. We need to come up with a way to describe it differently. But first off, we have to understand that because things can take on a huge number of values, it's very hard to know empirically what we know about any data. What we can do is we can sample, and all of a sudden this idea of x bar, an average or a mean, becomes very powerful. In addition, when you have a set of data, there's something called the variance and the standard deviation of the data. And it has a very particular meaning because what they are doing is they are somehow going to explain what's going on inside of a theoretical continuous distribution. It's very hard to know the entire population of an infinite distribution. So the empirical use of averages, of histograms, becomes extremely powerful. You need to have enough data, though, to make it appear that you understand something. And so studying continuous type data, where it can take on any value, with empirical finite distributions is an interesting dilemma. Now I want to point out this is not hard to resolve. When you decide to talk about probabilities on a continuous function, we just talk about probabilities of some event where if it doesn't contain an interval in it, we really don't get a positive value. So this thing needs to have somehow an idea of length inside of it. Later on, those of you that go to graduate school, you'll discover it's an idea of what we call measure. So it's very likely that people confuse a 0 probability with impossible. X equals 1/2 seems to have a 0 probability in a continuous setting, but you actually might get it. It's not impossible. Now, intervals, they have a positive probability. But an interval out here, which is impossible, still is 0. So impossible doesn't mean that the probability is 0. Yes, it does, sorry. Impossible means the probability must be 0, but probability of 0 doesn't mean that it's impossible. So the continuous world is going to be a bit odd. Now, because the continuous world, being a bit odd, requires us to define everything again. What does it mean to have a probability? So we're now going to have a function f of x, which is continuous, and it can be on intervals. It can be broken. So it could look like this. Now, I really don't want these lines here. This to just show me where they start. You could have a function that takes on, let's say, 1 over b minus a half and 1 over 2 d minus c. So this function could take on any value between a and b, any value between c and d. It has a uniform probability on those, and it has 0 outside. So that's why I drew this line. Kind of looks. So there could be a function, and I extend it to all of the real line. By just forcing the places I haven't defined it to be 0. So it's pretty common that when you have a continuous function, we'll define it over all the reals or all the positives. Now, why in the world did I make these heights here what I did? Well, first off, we like probabilities to be greater than or equal to 0, right? But in the continuous world, no. We need the integral on an interval of the function greater than or equal to 0 for all intervals. That's what we're going to require. So we need a positive valued function, or 0. So these are not to be viewed as the probabilities. This is the probability of the interval. That's not the probability. So we still will say that the probability density function, f of x, is greater than or equal to 0. But the associated probability will be done by an integral. That's how we define them. So if you take a look at what I did up here, b minus a is the length of this integral times 1 over b minus a times 1/2 is 1/2. This is area 1/2. This is area 1/2. Why, the total integral over the real line of the function is going to be 1. So it's all of the probabilities add up to 1. This is like a die that produces numbers between 0 and b, or c and d, but nothing else. And last but not least, if a and b are disjoint, then the integral over a union b is the integral over a plus the integral over b. So we get the sum of the discrete value. That's just like the sum in discrete values of disjoint sets. We have the same property here. Now, because probabilities that were defined before with sums are really what's the basis of integration, it looks like everything that we stated before should still work. So, what do you think our idea of expectation should be? Well, let's start with the uniform probability distribution function, which is continuous. So I'm going to let f of x be equal to 1 on 0, 1. F hat of x, now I'm going to extend to the real line. It's 1 on 0, 1, and it's 0 elsewhere. So this function looks like this. And now, seems to me that the idea of middle, the idea of average, should be that the number 1/2 seems to be right in the middle. In fact, it seems to even be a fulcrum point, a balance point. Let's see if we can just guess at what the expectation of x might look like if we had the definition that probability is done by x f of x, but integration. So what happens if we do this? If we do the integral, this is the value covering all values of x in the sample space of x times f of x dx. Well, f of x is just the number, this should be on the entire real line. Sorry, minus infinity to infinity of x, f of x. But since this function is 0 off of 0 to 1, this part of the integral is 0 because this is 0. This part of the integral is doable because f of x is 1. And this part of the integral is 0 because this is 0. So it boils down that the fact that we extended our function f to f hat, we say we've extended the function to the entire real line, it still boils down to doing the original f of x on its defined integral. But now f of x is just the value 1 on its integral, so the integral of x from 0 to 1 dx is x squared over 2. Evaluated from 0 to 1, lo and behold, indeed we get 1/2. So now the question becomes, is our understanding of the discrete average and the continuous average equivalent? How do we have an understanding of an average? For example, if you take your test scores, one way to calculate the average is move the values around. Take away 4 from here and get 88, put 4 there, get 88, and you right away get your averages 88. I don't think I can do that with continuous stuff. That's just discrete values. So what is the meaning of the average? Well, why don't we look at the following? Let's make a fulcrum. Let's put a fulcrum at 88. And 4 over from 88 is 92. And you have one test there. You have one test at 88. And you had one test at 84. It seems like if each test, excuse me, had the same weight, look at how the word weight that we use all of a sudden seems to have a physical meaning. Each test, if it had the same weight, this is balancing. It's pretty crazy. Now, those of you that have physics, we can do a harder one. Let's do 80, 92, and 88. We don't know where that balance point is, but I'll put 1 pound at 80, 8 over, I'll put 1 pound 92, and 4 left, I'll put 1 pound at 88. It doesn't seem it's going to balance here. The 80 is farther away from the 88 than the 92. Looks like the balance point's going to be here. Do you remember how to calculate a balance point? Let's see if we can figure this out. Let's see if the borrowing process here works and we can see what's going on here. So I'm going to borrow 6 from here. And what, get 86 and 86. I'm going to borrow 1 from here. I got 87 and 87 and 86. If I take a third and a third, I get 86 and 2/3. Ha! That looks to be the average. Now, does this average seem to be a teeter-totter weight? Well, some of you that took physics may remember torques, that Archimedes said, give me a lever and a place to stand and I can move the earth. I'm going to calculate some torques here. I'm going to calculate how far 80 is from 86 and 2/3. Why, that's 6 and 2/3. And I'm going to take 1 times that negative value, and I'm going to say that's pulling down here by this torque. Now I'm going to see if it balances with the other ones. 88 How far is that above here? That's 1 1/3 above. So I'm going to take the weight of 1 times the lever arm of 1 1/3. And I'm going to take 92. Now, how far is 92 above 86? Well, that's 5 1/3. I'm going to take 1 times the lever arm of 5 1/3. And I'm going to ask, does this balance? And the answer is, well, yes. 6 2/3 plus 1 1/3 plus 5 1/3, 2/3 is 0. In physics, we would say the torques are balancing. It really does seem that our concept of average that we had earlier seems to be a fulcrum, a center of mass. And that seems to be one way to describe this, that expectation is centered. Now, how many simple types of distributions can one make up? Well, one can make up a bazillion. So first off, it's true that if we take f of x to be any positive valued function, and let's do it on some finite interval. You do this. Here's an a to b. We can immediately make this into a probability density function by adjusting it in the slightest of ways. First, I'm going to integrate this function over the integral I and get its area. So first I find its area. Works out nice. Now I define a new function that is 0 to the left of A, 0 to the right of B, but on this interval I'm going to make it 1 over A times f of x. And if I integrate this over its whole range, that disappears, and the integral of f hat on I becomes 1 over A, the integral of f on I, which is 1 over A times A, which is 1. And just like that, this function, which had some value, was easily adjusted to a real function that's now a probability function. Now, some of you may remember Calc 2 to Calc 3. There was things called balance points, center of masses. Wonder if they're associated with averages, expectations. That would be very interesting. But let's not do that just yet. That was more multidimensional. Let's just ask ourselves, what other types of continuous probability functions can we come up with? Well, it's clear then that if f, its support, exists on a finite integral, then we can immediately extend it so its domain is on the real line and it's a probability function. But what about those functions that exist whose domain is infinite? How are we going to adjust them? Well, the answer is we're going to do the same trick, and let me give you such a function. Let's take f of x, whose domain is 0 to infinity, and let's make it look like this. One such function might be an exponential decay function. Let's do 7e to the minus 3x. Now, you know the limit of f of x as x goes to infinity is 0 because of the negative exponent. You know that its height here is 7. You also know that you can do the integral of this on 0 to infinity, and the 7 comes out. Integral of e to the kx is 1 over ke to the kx, so it's minus 7/3 e to the minus 3x, and evaluate it from 0 to n, and then we'll take the limit as n goes to infinity. We still need to do a limit. Well, we plug in n, we get minus 7/3 e to the minus 3n minus 7/3 times 1. Now when we take the limit as n goes to infinity, this goes to 0, and lo and behold, we get 7/3. there is a finite area here. Well, just like in the finite case, we get a finite integral. As long as I get an a that's finite, I can extend this. Guess what? It's going to be 3/7 of 7e to the minus 3x on 0 to infinity, and it's going to be 0 off 0 to infinity. And this function now has the property that f hat of x is greater than or equal to 0, and the integral over the real line of f hat is 1. I've adjusted it and made it a very nice integral. That means we can talk about this as being a PDF, a probability density function on this larger range. And we can ask about the expectations. So, if we can ask about the expectation of x, what would be a reasonable definition of the expectation of a function of x? It's not mu, it's an m of x. Well, seems to me we just take that m of x times f of x and integrate it over the real line, provided this f hat has been extended and you reduce it to the right one. This seems like a very natural definition. With that natural definition, do you think it's going to be the fulcrum for this function, the fulcrum for another function? Is it going to work? Is it going to be, somehow, is the expectation going to be the middle in terms of a balancing act? That would be really nice. That way we have a physical understanding of these. Okay, now, how many continuous functions are really going to be of great interest to us? Well, first off, there's that one that took place uniformly on interval. It's called the uniform continuous function. Then we just did this one, the exponential. So we have the uniform. This turns out to be the exponential distribution. But what's really interesting is you've seen it before. We've talked about it. We want a one-humped curve. We'd like to understand what we've seen a million times. Where are we heading? We're heading to understanding very strange curve. This beautifully symmetric, one-bumped curve. As long as its original integral is less than infinity, we're going to make it have an integral of 1. It's going to be a distribution. It's going to have a center value. It's going to be symmetric. But how do we pick the correct one? There are lots of these. Which is the right one? And what's very strange is we're going to develop the theory of what is the right function to describe a normal. When we say normal, it is a commonly occurring occurrence, and we want to know what function that is. All right, there's our beginnings of our continuous distributions.